So today I'm going to describe some new tools for estimating treatment effects in the presence of high-dimensional or non-parametric nuisance. And this is pretty new work. I'd love to get your feedback, and I'd love to get your perspectives on anything I talk about today. And this project came out of a conversation that I had with Vasilis Tsirtanis. Vasilis is a colleague of mine at Microsoft Research. He studies machine learning and economics and algorithmic game theory. And the conversation went a little bit like this. One day he came over to me and said, "Lester, I love double machine learning." And then I said, "What?" And he said, "It's a tool for accurately estimating treatment effects in the presence of many potential confounders." And I said, "I have no idea what you're talking about." So he said, okay, let me give you an example. So this is the example that he gave, and it's estimating price elasticity of demand. That is, estimating how demand changes when price changes. And so this sort of thing certainly comes up if you work at a tech company like Microsoft. It also comes up if you're a food distributor and you want to know how to price different products. And it even comes up if you work for the World Health Organization or the World Bank and you're interested in the effect of a tax on tobacco consumption, on purchasing cigarettes. So how do you go about doing this estimation? Well, typically you collect some data, data involving prices that were set and the amount of demand that responded to those prices. And so you might have a data set like this. It's a pretty small data set, but it's a data set. And so what's the first thing you might do? Well, you say, okay, well, if I want to predict elasticity, I should just regress log demand onto log price. So here's our regression model. Y is log demand. T is the log price, the treatment in this experiment. And the coefficient that relates them is going to be the elasticity, ideally. And so you might just say, I'll just do an ordinary least squares regression, and I'll get a best fit, and that will be my elasticity. So what happens in this example if we do that? Well, here's your best fit line. And if you read off the slope of this best fit line, it tells you that increasing price increases demand. And that seems problematic. It doesn't quite jive with our intuition for how demand and price work. And so what happened here? Well, what happened is that, like in most pricing problems, actually, there's some degree of seasonality. So these points that are collected up here are actually from the winter, where demand is higher. Demand often increases in the winter due to big holidays like Christmas and Black Friday, if you consider that to be a holiday. And the points down here were in fact collected in the summer. And so what happens? Well, here we have a case where we don't actually have the price affecting the demand. We actually have the demand affecting the price. So everyone knows that demand is going to go up in the winter, and they've adjusted their prices accordingly to account for that. So that's a problem, and this is a problem from essentially our regression model. And so how could we fix this issue? How can we account for the fact that we have this seasonality? Well, one pretty easy way is just to introduce a confounder, the season, as a variable into our regression model. So now I have an indicator variable, this extra covariate x. It also has a coefficient, and now I've accounted for that, that potential confounder, something that affects both price and demand that I didn't account for before. Okay, so now what happens if I rerun my regression? Well, then I get something like this, because the indicator I can have the split point, and the coefficient, the elasticity coefficient that I fit is actually pretty reasonable. In this case, it's a perfect fit to my data, but of course, it's a very artificial data set. Okay, but this, you can take my word for it, this fixed this particular problem. But in this case, we're only dealing with a single confounder in an artificial data set. What if there are hundreds of confounders? What if there are thousands of confounders? And actually, that's the typical case these days. On top of seasonality, is it winter or summer? We care about the time of day, we care about the day of the week, we care about the month. We observe purchase histories, past purchase histories from customers if we're a business. We observe your browsing history if we're essentially any website that you use. We take into account other product prices, and we care about how those impact price elasticities. We take into account demographics. We might even take into account the weather. And these are all things that we routinely collect that's readily available. And it's likely that at least some of it does impact both the price and the demand. That is, at least some of these things are likely confounders. So how do we deal with all of those things? And this is the question that Vasilis was posing to me. This is why this example came up. So how do we deal with all of those things simultaneously? Well, okay, so here's one option. Here's what you might call the classical option. We could estimate the effect of all of the potential confounders really well. So that's option 1. So here again is our regression model. We have our log demand y, we have our log price t. We care about the elasticity, but then now we have all of these other confounders. That's this whole vector x, and they have some effect on the potential. They have some effect on the log demand. We'll call that f0. So this is some function relating the confounders to the outcome that we don't know, but in some sense we have to care about because it affects the answer. Okay, so what we know from just standard asymptotics is that if we could estimate f0, this nuisance function, at an n to the minus 1/2 rate, then we can also get a good estimate of theta 0. So that's all we have to do. All we have to do is estimate all the effects really well, and then we'll get a good estimate of the elasticity. But that seems kind of problematic. Typically, accurate nuisance estimates are unavailable if f0 is high dimensional, say linear and high dimensional, or if it's non-parametric. So what else can we do? Well, this is where that double machine learning comes back into play. So this is an idea due to Chernozhukov and colleagues, although it builds on a lot of past work of a similar flavor. And the idea is that we can get a somewhat poor estimate of the nuisance function f0, and then account for that. So when we estimate theta 0, we're going to do it in 2 stages. So first we're going to estimate f0, then we're going to estimate theta 0. We're going to do it in a way that's somewhat robust to errors in that first stage. So we're going to use what's called a Neyman orthogonal estimator to be robust to the errors in our estimate of the nuisance. Okay, so what does that buy us? Well, specifically what their theory says is that an n to the minus 1/4 estimate of f0 is sufficient to get a square root n consistent estimate of treatment effect, of your elasticity in this case. So that's good. That's a pretty big gain. We're not demanding the same level of quality from our nuisance estimates as we were from the estimate that we cared about, the target parameter. But I think it also raises a lot of questions. So for one, why n to the minus 1/4? Where does that come from? Can you relax that? When can you relax that? And how can you relax that? So these are all the sorts of questions that I want to deal with today.
Excuse me?
Yeah.
Sorry for the naive question, but
Yeah.
why restrict yourself to this regression model? What if you used a tree-based model?
Okay. So I didn't even explain what I meant by machine learning and this double machine learning, so that's a great question. So the regression model, so there's, in this model, we only have, there's one parameter that we care about, theta 0. And so in some sense, you could use a tree-based method, but regression, if I had a good estimate of f0, then doing just something like linear regression would work very well for this model. And you could change the model slightly to account for other relationships between t and y. But where the machine learning comes into play here is that you're going to use your favorite machine learning methods to get an estimate of this f0. So those could be tree-based methods, they could be neural networks, whatever you want. And the idea is that if you can get a good estimate in terms of prediction error of f0, then you can also get a good estimate of theta 0. And I think you're asking, why is the relationship between t and y so constrained?
Yeah.
In a lot of cases, it's because t is just a binary outcome anyway. And so this is as general as you're going to get. You're just learning one parameter, which is if you are treated, then it has this effect on log demand, and if you're not treated, you have another effect on log demand. But mostly it's just, for today, it's just for the simplicity of presentation. Nothing we're doing relies particularly on this model. I'll present a number of specializations of our results in this setting, but we're actually going to be working in a general setting of generalized method of moments. So you could have a tree-based relationship to it. Yeah. What I really want to highlight about the relationship between theta 0 and f0 here is that often the parameter that you care about, the relationship you care about, is something that's intrinsically low dimensional, something that's pretty simple, and the thing that you don't know is much more complex. And so in those sorts of cases, you want to get really good estimates of the simple thing without having to get really good estimates of the complex thing.
You're not worried about theta 0 being 0 when you choose a sufficiently complex model in f0?
Well, it could, and that's often what you're doing is something like a test. So you're doing a test for association. Condition on everything else that I've tried to, condition all those confounders, does it still make a difference? And if it doesn't, it means your treatment didn't really matter. So I am worried about that, but that's important. That is something that we care about. Okay, So what are we going to do in this talk? I'm going to give you a framework for a generalization of this Neyman orthogonal estimation. So it's K orthogonality. And roughly what you get from this is that n to the minus 1 over 2k plus 2 consistency for your nuisance estimates implies root n consistency for your target parameter. So by employing this higher order notion of robustness, you can actually do a worse job at estimating the nuisance and still get a good estimate of your target parameter. Then we'll talk about when these kth order orthogonal moments actually exist. And so for that, I'm going to focus on the partially linear regression model that's common in causal inference and give you a characterization of this. So cases where these moments don't exist and also where they do exist. And where they do exist, I'll give you some explicit construction of second order orthogonal moments and show you how they work in practice. Okay, so I need to explain a lot of things. For that, let's get a bit more abstract. So this is the general problem we're trying to solve, an estimation with nuisance problem. There's a target parameter theta, it's an r to the d. Think of these as the elasticities. There's some unknown nuisance functions that also impact the outcome of interest. And we're going to try to estimate the target parameters given independent replicates of a data vector. In this case, I have a data set of size 2n. It's 2n because I'm going to split it in half at some point. So let's keep that 2 around. And to give you an example of what this data vector might look like, this is going to be a running example throughout the talk. I'd like you to consider this what's called the partially linear regression model. So T here represents a treatment or a policy that's applied. So you could think about it as the log price in our example. Y is going to be an outcome of interest, the log demand. And X is going to be a vector of associated covariates, like seasonality or other potential confounders that could impact both the treatment and the outcome. And under the partially linear regression model, all these variables satisfy the following relationship. So we have essentially two equations. One looks very much like the one I've been displaying to you. So the linear part is the relationship between t and y. The partially part is this f0, which is not necessarily linear. And there's a second equation that governs how the treatment is impacted by the different confounders. So again, there's a nuisance function. So the nuisance functions here are f0 and g0. And the parameter you care about is theta 0. And epsilon and eta are just noise variables in the model. Okay, so we'll come back to this model again and again. But what else how are we actually going to go about estimating our target parameters? So we're going to use what you could call two-stage z estimation, or two-stage method of moments. And so to do this, we need some moment functions, m, that identify the target parameter. And so identify in the following way, it should be the case that m is a function of your data, z, it's a function of your target parameter, theta 0, and it's a function of the output of your nuisance, h0. And it should be the case that on average, when theta 0 is plugged into m, the value is 0. So it's mean 0 when theta 0 is plugged in, conditioned on x, your covariates. And you also want it to not be mean 0 when theta is not equal to the truth. And this is the identification part. Okay, so we have this conditionally mean 0 moment function at the truth. And how do we go about doing estimation? So we're going to do, first just an example. In our PLR model, typical example of a moment function would be just the score function that you get from ordinary least squares. So if I already knew the nuisance f0 and I wanted to estimate theta in the PLR model, I might just do a least squares regression. This is the derivative of the least squares objective with respect to theta. And setting that equal to 0 on average is what you would do to solve the least squares problem. Okay, so that's the PLR model example. Actually, it's just worth saying that this is one moment function for this problem. A big focus of the talk will actually be on constructing better moment functions for this problem that have better robustness properties than this. Okay, so two-stage z estimation with sample splitting. How does this work? So in stage 1, we're going to estimate the nuisance however we like. So we'll use our favorite machine learning method, some non-parametric regression, some high-dimensional regression. Somehow we're going to get back some estimates h hat of the nuisance h0. For this, we're going to use the second half of our data, so data points n plus 1 up through 2n. Now, to fit theta, we're going to plug h hat into the moment function And then we're just going to solve, and then we're going to do z estimation. We're going to find the value of theta that sets the sample mean equal to 0. This sets the sample mean of the moment function equal to 0. So it's standard z estimation. It's two-stage because we didn't know what the nuisance was ahead of time, so we plugged in an estimate of it. This is called the sample splitting approach to two-stage z estimation because we were using the first half of the sample to estimate h hat, and we're using the second half to do this to find theta, to find the final estimate of theta, which I'll call theta hat SS for sample splitting. Okay, so there's some drawbacks to using sample splitting in this way. It's statistically inefficient. Often what's impacted is the first stage because that's usually the harder part of the, the second part of the problem is pretty easy. In the PLR model, we're fitting one parameter. That's a pretty easy thing. But the first part is impacted by using less data. So how do we deal with that? Well, there's a second version of this two-stage z estimation that Chernozhukov et al. Advocate in their double machine learning paper, which is called cross-fitting. And the idea is that you split your data into k batches. You fit k different estimates of your nuisance parameters, so each one withholding the data from one batch. So I'll call the batches I1 through Ik. So I fit capital K different estimates, h hat k. And then when I choose my final parameter, I plug in the nuisance function estimate that did not use the fold that my data point is coming from. So for every data point, zt, xt, I'm only using an estimate that was based on other data. Independent data in this case, because the data points are IID. And roughly because a lot of the analysis is going to be asymptotic, and we have asymptotically linear statistics, this actually mitigates the effects of sample splitting, and we regain the efficiency that was lost. Yeah.
Like by analogy to like debiasing, is there a way to see why here the independence is necessary, but in debiasing it wasn't?
It's not necessary. So you don't have to go through this route at all. You could use other arguments, just directly argue about training error, but this works a lot better in practice.
I see.
So yeah, if you compared the sample splitting version to this version to a version where you just use the same data on both iterations, this works much better.
But the other one's also analyzable.
The other one's also analyzable, and asymptotically, they're all good.
Okay, sure.
Yeah, and so I think there's some very close parallels between this double machine learning literature and the debiased Lasso literature, so I'll come back to that at the very end. Okay, so now we have our estimators. Theta hat CF is the cross-fitting, theta hat SS is sample splitting. Our goal is going to be to establish root n asymptotic normality of these estimators. So I want root n consistency, and I want them to be asymptotically normal estimates as n goes to infinity. This will allow us to do asymptotically valid hypothesis testing, for instance, association testing, condition known covariates, and also to establish asymptotically valid confidence intervals. Okay, so the real question is, when can I get this? And in particular, what moments do I need to use to achieve this? Well, let's start with what the double machine learning literature suggests, which is first-order orthogonal moments, or what you might call Neyman orthogonal moments. The idea is that on top of having your moment function be mean 0, you want its gradient with respect to the nuisance parameters to also be mean 0. All right, and that's what this definition says. The gradient with respect to the nuisance parameters is also mean 0. This is a principle that actually dates back to the early work of Neyman, who was developing better unbiased tests in the presence of nuisance. Although it's had several developments since that point. And essentially what it does is it grants first-order insensitivity to errors in the nuisance. If you do a Taylor expansion of your moment function around the nuisance, and around your plug-in estimate of the nuisance, the first-order terms just go to 0, or are 0 on average. And so now the error is actually dominated by second and higher order terms. And that's the value that you're getting from introducing these first-order orthogonal moments. Now, interestingly, this property is not satisfied by the standard moments that you'd get out of least squares, the moments that I shared with you before. But it is satisfied by, and sorry, this is under the PLR model, so I'll keep coming back to that example. So under the PLR model, it's not satisfied by the moments I shared with you before, but it is satisfied by these modified moments that are both discussed in the Cherno-Zhukov paper, but have a much longer history. Okay, and so the main result of Cherno-Zhukov et al. In this setting is that if I can get n to the minus 1/4 estimates of the nuisance, and I use first order orthogonality for my moments, then I get root n asymptotic normality. So instead of having to fit all my parameters well being at root n rates, I only need n to the minus 1/4 rates, and life is still good. So you might ask then, oh yeah.
Sorry, quick question. Do you know G, or do you also need to estimate G here?
You also need to estimate G. So this is n to the minus 1/4 estimate. So whenever I say H, it's all the nuisance, and now the nuisance is both F and G. It's a good plus check. Okay, so you might wonder, how do we go beyond that? And it seems like there's a natural way to iterate this process. We just got rid of the first order Taylor expansion terms. Let's just get rid of more terms. And so that's what we're going to call K orthogonality. So we want your moment function to not just be mean zero and have gradient mean zero. We want higher order differentials to also be mean zero. So we're using the differential operator. Essentially, we're saying partial derivatives of order K and below are zero on average. That's what K order orthogonality is. And again, the intuition is that we want to kill terms in a Taylor expansion around the true value of the nuisance. Okay, so what does this buy us? Well, here's a result from our work. And it says that if you use K orthogonality, and you have your standard identifiability and regularity assumptions about your moments, then n to the minus 1/2k plus 2 estimates of your nuisance are sufficient. So there are a few things to unpack here. First, you get root n asymptotic normality. I've given you an expression for the covariance matrix. So it depends on a couple of properties of your moment function. It depends on the covariance of your moment function, and also on the inverse of the gradient of your moment function with respect to theta. And we'll come back to that later, because it will turn out that when these moments don't exist, or when useful moments don't exist, it's typically because this value is zero, and hence your asymptotic covariance would be infinite. Okay, well, we'll come back to that. There are a couple of just remarks to make. So I've said that you want every nuisance function to have this rate of decay. Technically, the analysis only requires that products of the nuisance functions have to decay. So if you estimate one really well, you can afford to estimate another one more poorly. This is kind of a double robustness type property. You can prove similar results for non-uniform orthogonality. So you don't actually need all of your second order moments to be orthogonal. You could just pick and choose, and you'll still get some benefits from that. And finally, what's worth highlighting about the result is this holds the promise of coping with more complex nuisance functions with less data. But of course, that's only a useful promise if these moments actually exist. So how do we construct K orthogonal moments in practice? That's what we'll turn to next. Or actually, here's a more basic question. Can we construct K orthogonal moments in practice? And I'll just remind you, this is our partially linear regression model again. So we're going to focus in on this model and try to characterize K orthogonality in this setting, or at least 2 orthogonality in this setting. And it turns out that the answer is sometimes. And in particular, if your treatment residual in that second equation, the eta, is Gaussian, technically conditionally Gaussian given x, but if it's Gaussian, then there's no 2 orthogonal moment that will yield root n consistency. Okay, and so you can actually prove that, yeah.
In the covariance in the previous slide,
yeah.
it's independent of k.
It is and it isn't. So it depends on m, and the m has to satisfy your K orthogonality property. And so different m, you'll have to choose a different m for each k, typically. Yeah. And so the result of that, and this is worth mentioning, is that essentially what you're doing by introducing this orthogonality is you're reducing bias, but you're going to pay for it in variance. So typically your variance is going to go up, but you're also going to be able to handle more complex settings that you otherwise wouldn't be able to deal with. So there's a bias variance trade-off there.
Possible to somehow see how the variance is from with k, or what's the best gain versus the variance?
That's great. So I think we'd have to say something a bit more explicit about exactly what moments you're using, and if there is, an explicit. So you might think, given, and I believe this is true, like given a, k minus 1 orthogonal moment, there is a natural k orthogonal moment, and then you'd be able to trace out that variance with k. But this is really saying pick your favorite k orthogonal moment of any type at any point, and this is what your expression will look like. So it's hard to do that comparison without being more explicit. That'd be very interesting. Okay, so, right. Oh, right. We had this negative result. Oh, yeah, that's sad. Okay, so we use to show this, we use Stein's lemma, and so what this lets us, which is essentially just integration by parts. So this lets us show that if you're two orthogonal, then this derivative with respect to theta of m is also going to be 0 when your treatment residual is Gaussian, which means that if you were root n consistent, you'd have infinite variance, infinite asymptotic variance, which means that you have a pretty useless estimator. So that's bad. But in our pricing setting that motivated all of this, non-Gaussian residuals are actually typical. So a typical sort of pricing setting scheme is that you have a baseline price, a baseline log price, and you introduce random discounts like 10% off, 25% off through Sunday. These are actually discrete perturbations of your baseline price, and they're decidedly non-Gaussian. So there's still hope for getting gains out of our second or higher order orthogonality. So we're going to come back to this question again of, how do we actually construct k orthogonal moments when we can? And what we learned from the last slide is that if we want to do this, we'll have to exploit non-Gaussianity somehow. Here's one characterization of Gaussianity. Eta is Gaussian, so a Gaussian distribution is defined by its moments, and the moments satisfy these particular conditions. So eta is conditionally Gaussian given x, if and only if it satisfies these moment relationships for all integers n, or all integers r. So what we're going to do is try to exploit the violation of one of these conditions and construct moments that work well when that condition is violated. So here's the result. If you don't satisfy this condition for some r, and hence you're not Gaussian, but this in a particular way, you're not Gaussian in this particular way, and if I know essentially the rth moment of eta, then the following moments are two orthogonal. This is what they look like. There are a couple things worth noting about this. First, I've actually introduced another nuisance function. So before we had f and g, q is a linear combination of f and g, so now we have q and g. But I introduced this new nuisance function, which is basically the conditional r minus first moment. So it's again something that we have to estimate, but it's still two orthogonal, so I can get this pretty poor n to the minus 1/6 estimate of it. But on top of that, I've actually required that you know something that you didn't have to know before, and that is this rth moment. So that maybe is a little bit annoying. If you know the rth moment, that's great, then you just go and happily use this. That's maybe a little bit annoying. So what can we do if we don't know that? Well, if you don't know that, there's a very similar moment function you could use that I would say what I would call almost two orthogonal. So instead of saying that you know the rth moment, we're just going to make that another nuisance function too. And these moments are two orthogonal with respect to almost all of your partial derivatives, but there are a couple of partial derivatives that don't enjoy orthogonality. That's the pair between q and mu r, and the pair between g and mu r. So there are a couple of pairings that don't satisfy orthogonality. And essentially what this means for us is that I need to estimate mu r at a faster rate. So if I can estimate, so exactly what we need for this case is if I can estimate mu r at an n to the minus 1/3 rate, and I can estimate everything else at an n to the minus 1/6 rate, then I still get my asymptotic normality. Okay, so we're still doing better than we were before, where everything had to be n to the minus 1/4. In particular, I'll show you that estimating mu r at an n to the minus 1/3 rate is typically not hard. It actually gets easier when r is higher. Okay, so to demonstrate that, let's specialize this to the setting of high-dimensional linear nuisance. So we've been carrying around these nuisance functions, the f's and the g's. I'm going to make them linear functions now, but potentially high-dimensional ones. So ones where I have tons of confounders, and that number can be growing with the number of data points. All right, so now I have the linear function x with parameter beta naught, and linear function x with parameter gamma naught entering into my equations. And the question we want to ask is, how many relevant confounders can we tolerate? If these, I can't expect to estimate all of these parameters if they're all relevant, but if these functions are sparse, if the parameter vectors themselves are sparse, I can hope to still do good estimation and get good treatment effect estimates. So for instance, I could use the lasso. So I could use the lasso to estimate beta naught and gamma naught. What does that give me? It just typically gives me error that looks like square root s log p over n. Okay, so what does that mean? If I just rely on zeroth order orthogonality, if I just use my typical least squares moments, that means I need s to shrink with log p. To either be bounded if log p is bounded or to shrink with log p to get my root n asymptotic normality. So that's not great. If we use first order orthogonality, where I need only n to the minus 1/4 rates, I can actually let my sparsity grow. So I could, if I'm in a setting where I actually want to use nonlinear functions and I'm doing basis expansions, this lets my sparsity grow at a rate of n to the 1/2 over log p. So that's good. That's much better, and I can support much more complicated functions that way. Now, what we can show is that if you use these second order orthogonal moments and particular estimates for all those nuisance functions that I mentioned, that you can actually get away with n to the 2/3 over log p instead of n to the 1/2. So this is how it works. You're going to estimate the parameter vectors gamma naught and q naught. Q naught here is a linear combination of beta naught and gamma naught. You're going to estimate them both with the lasso. They're both sparse. You're going to estimate the unknown moments in a particular way. You're going to do some additional sample splitting. So you're going to take your first stage sample, which had n points. You're going to break that into half. You're going to fit the lasso estimates on half of it, and then you're going to use the other half to estimate the second and third moments in the following way. And it turns out that those satisfy all of those convergence properties. In particular, this is n to the 1/3 consistent, and this is consistent at a faster rate. And so if you plug those in, the choice of r I made in this case is 3. You know, there's a different set of moments for different choices of r's. The choice of r made in this case is 3. Then you get your root n asymptotic normality. Now, I should just note, though, that there's a condition. And the condition here is that you're, again, violating Gaussianity in some ways. So in this case, you have to have excess kurtosis. So this condition says if you have excess kurtosis, then this will work. Then you get root n asymptotic normality. If you picked r equals 2, then the condition is that your skewness is not 0. If you pick r equals 4, you get another condition depending on a different moment. Okay. So we implemented this. How are we doing on time, by the way?
For about 10 minutes or so.
5 minutes? Thanks.
5-10 minutes. Oh, yeah.
20 minutes? Yeah.
So the assumption is x has normal 0, 1 entry is crucial.
Oh, sorry, yeah. So there are a bunch of other assumptions here. These are all just assumptions that we picked that make the lasso work. You could use other things here, too. This was just yeah, roughly anything that makes the lasso work. There are a few other technical conditions, but these are not really essential to the orthogonality part of things.
So basically, it means for confidence interval in high-dimensional linear regression, you can beat all the previous results if the conditional distribution of the variable I care about, condition on the others, is not Gaussian. Is that?
So that's.
Am I translating correctly?
That's what it seems like.
Okay.
And so we'll come back to that too, because I wonder. So we know there are known lower bounds for doing this sort of thing, but those lower bounds all seem to assume Gaussianity. Yeah. So I think that's a really interesting question. Like, can you beat those lower bounds by getting out of Gaussianity?
Yeah.
Yeah. Okay. So we implemented this. We're trying to. These are all what I'm going to show you are all simulations, but they're trying to mimic this price elasticity of demand setting. So t is representing our log price. We're drawing eta from this discrete distribution representing random discounts over that base price. And here are just some results. So here I'm comparing the distribution of, and so I'm estimating theta 0 here. That's my target. That's my elasticity. So I'm showing you the distribution of my elasticity estimates when I either use first order orthogonality, that's double machine learning, or second order orthogonality, where the nuisance is fit via the lasso. And so in this case, the true value that was used to generate the model is this blue line, is at the value 3. You can see here that we have a lot of bias from the first order. So first order is on top, second order is on the bottom. We're getting a lot of bias. And the bias is actually an order of magnitude larger than the variance. Okay, so it's like, it's pretty concentrated, but it's pretty concentrated about the wrong value. By employing the second order in this case, your variance does increase somewhat, but it does get rid of your bias. Yeah.
So what kind of x are you generating in t? An epsilon something?
Oh yeah, so I'm following all the prescriptions of this, this theorem. So x's are IID Gaussian. The epsilons are uniform in a range minus sigma to sigma. Are there other? All right, so here's a breakdown of bias and variance. And so this is basically what you expect. You're seeing that as your support size, as the number of relevant confounders grows, the bias of the first order method is growing pretty quickly, whereas the second order method is growing in a very shallow way, not that much at all. But on the other hand, the standard deviation of the first order is pretty consistent, whereas the standard deviation of the second order is growing. And so there's a trade-off here. And in this case, though, the trade-off is still in the favor of second order. So the overall MSE is actually much higher for the first order than the second order as your support size grows. So here's some plots from different settings of n and p. So before it was n is 5,000, p is 1,000. Here's n is 10,000, p is 1,000. We see a very similar picture. Here's n is 5,000, p is 2,000. And you see a similar picture until, at this point, there's some sort of crazy numerical instability, and the error just shoots up to something like 6 or goes off the plot. We think this has to do with the fact that when you solve that second stage equation, you can get values that are actually very close to 0. And then if you're not doing anything to control for that, you can get arbitrarily large estimates out. So you're getting some sort of instabilities when your denominator in that second stage estimate is near 0. Okay, here's varying the noise level. I mentioned that epsilon was uniform minus sigma to sigma. So this is what happens as you vary that noise level. And I think I just want to leave you with some opportunities for future direction, some of which have already been surfaced in the conversation we've had so far. So first, for second order orthogonality, how do we select optimal moments, or if not optimal, improved moments than the ones I gave you today? And how do you construct moments for other causal inference models? I mostly focused on partially linear regression. For kth order orthogonality, when are they available? I only really explored second order here. When can you do third order or fourth order? And when are they useful? And how do we construct them? We talked a little bit about lower bounds. There's this very related literature on lasso debiasing. And out of that literature and some of the statistics literature, we actually have lower bounds for these sorts of problems. But they often assume Gaussianity of the covariates, of all the covariates, including, in our case, the treatment variable. So I think an interesting question is, can you beat that lower bound if you have a non-Gaussian covariate? And then, of course, I'm really interested in applications to other problems with non-Gaussian treatment residuals. So let's leave these ideas up for all of you, and hopefully you'll have thoughts about them.
So this theory doesn't necessarily depend on the target parameter being identifiable with the true causal parameter, even though the motivation is causal inference, or I don't understand that part.
So your moments definitely need to identify the parameter. And so in some sense, there has to be truth to the set of moments that, that is, identification does matter. Okay. Yeah.
So like theta naught is like the true causal.
It has to be the truth. That's right. Yeah.
More questions?
I mean, maybe I'm wrong. It seems like this is solving these things in practice might require some fairly large tensor type computations or things like this.
Oh, well, it depends on how big your parameters. In our case, the treatment effect is always a scalar.
But
And so it's really
the nuisance.
Oh.
parameters.
Well, our nuisance parameter estimates are just like fit lassos. And you could alternatively do something like fit boosted regression trees. They're all okay. So I should go. I didn't really talk about the nuisance estimation that much, but the reason why we use these particular moments is because essentially it boils the estimation of the nuisance down to, in the linear case, even in the nonlinear case, to just solving two regression problems. And so you only care about actually prediction error. You don't even care about parameter consistency for these results. And so to fit nuisance, essentially what you'll do is you'll regress y onto x, and you'll separately regress t onto x, and those are going to give you your nuisance estimates. And you do it using your favorite regressor, so it could be boosted decision trees or random forest, it could be the lasso, and that's what you plug in for your nuisance estimates.
But I mean, these cubic terms on t minus xy and
Oh yeah.
3t minus xy mu 2, like these don't matter?
Those don't matter. So those only matter, the moment actually only matters for the solution of theta. You don't minimize this moment function with respect to any of the other parameters. You just plug in whatever estimate you want of those parameters. That has to be good, good in the sense of n to the minus 1 over 2k plus 2. So you pick your favorite auxiliary way of estimating those things. Which is, I think, one of the advantages of the double machine learning framework to begin with, which is that it has this plug and play feature. Yeah. And then you only use these to fit theta, and this is linear in theta in this case.
And so for example, when you fit beta 0 for your guess of beta 0, you run the lasso on the model with both theta and beta 0. Then you pull out that beta 0, which is sort of reasonably consistent,
so you could do that, and if I use slightly different moment equations, that would probably be the thing you would do. So the reason why I reparameterize this as q0 equal to this funky linear combination is that instead of doing that, I'm just actually going to regress y onto xq. So now I don't have to separately keep a theta 0 parameter around. I'm just going to do the regression of y onto x. I'll get out a q hat.
And the reason for that is because t is linear.
Yeah, exactly. So it's reasonable because of that reason.
Nice.
But you could do what you said in the general case, and that's fine too.
Okay.
More questions?
So for CF, you're able to get efficiency in some way? Like you have a square root of 2n as opposed to square root of n?
Yeah, essentially, yeah.
That must be like a condition on how much you partition the data to your validation things.
Yeah, so as long as it's fixed and finite, so as long as so if you don't change it, you just pick k to any fixed number, then you'll get that, you'll recover.
K equals 2, you get
Even with k equals 2, yeah.
Really?
Yeah. But in practice, choosing more than k larger than 2 can be useful in practice. Asymptotically, you're going to get the same thing, but in finite samples, it makes a difference.
Okay, if there is no other question, we'll go for lunch.